So, good afternoon, everyone. We're here to actually talk about a project that was recently funded by the National Science Foundation. It's a collaboration between Kennesaw State University and the Algebra Project. And as it says in the title, we are looking at a process to really enhance the learning of middle school mathematics. One, using what we call a curricular process from the Algebra Project, but really blending that with a computational thinking framework, right, from CS. And this is the team, Alan, Brian, Deepa, and myself, that are working on this grant. I wanted to give, for those of you who may not know, just a lightning introduction to the Algebra Project. This is the founder of the project, Bob Moses. In the late 50s, Bob was actually a middle school mathematics teacher in New York City. And with the beginnings of the civil rights movement during the 60s, Bob decided to go south and participate. And in particular, he joined SNCC, the Student Nonviolent Coordinating Committee. Bob was the field secretary for SNCC in the Mississippi Delta. And of course, they were working on voter registration and voter education for the sharecroppers there. In the mid 60s, actually, Bob left the United States. He spent a little more than a decade, of all things, teaching mathematics outside of Dar es Salaam in Tanzania. And upon his return to the US in the early 80s, Bob was awarded a MacArthur Fellowship, right, this Genius Award, for the work that he had done with SNCC in Mississippi during the 60s. It was while he was under that MacArthur Fellowship that he began really the Algebra Project. And here's really the goal of the project. I think for Bob and for those of us who have joined the Algebra Project, we really see it as a continuation of the civil rights movement from the 60s. They did manage to open up the Democratic Party. They did manage to secure, voting rights for large portions of the population in the South. But the issue of education, right, was really not cracked in all of that, and in particular, whether every child in this country deserves a quality education, and in particular, a quality education in mathematics. So the project has developed a goal, which simply put is that we think all students graduating the K-12 system, and particularly those students that are most disenfranchised, that is, students performing in the lowest quartile in mathematics on state standardized exams, that we ought to be able to guarantee that they graduate from high school ready to do college or career mathematics without remediation. That is the goal that for more than 30 years we have been working on. And to really frame that goal in a particular way, this is something that I would like you to respond to in the chat, and I would ask Deepa to relate some of your thoughts. There are 4 features of a learning environment that those of us in this project are particularly concerned with. And it has to do both with the cognitive learning that students are engaged in, but also the social and emotional dimensions of that learning. And so what we've been thinking about and wrestling with is the degree to which reasoning, critical thinking is central to the work that students are doing in the classroom, the degree to which discussion is an integral part of the work that students engage in the classroom. But we have two other features we're particularly interested in also, imagination and creativity. Right? So what I would like you to do in the chat for just a moment is really for each of the major content areas, right, in school, English language arts, social studies, science, and mathematics, I would like you to at least rank from highest to lowest, and I'm most interested in those disciplines that receive a highest score of 1 or even 2. For those 4 disciplines, where do you think reasoning not so much should lie, but actually lies on a scale from 1 to 4? Which of those, 1 being the highest, for reasoning, is it best an integral component of the classroom in ELA, social studies, science, or math? Discussion, in where does it receive kind of, I guess, the highest score, right? ELA, social studies, science, or math. And these last 2, in particular, which one of those 4 would you rank as the place where imagination is most engaged? Which of those 4 would you rank as the place where creativity is most engaged? Deepa, do we have any responses in the chat around this ranking? Deepa, can you hear me? Let me stop the sharing for a moment to come back and see. Hello, Deepa.
Bill, I'm going to try leaving and coming back in. Will you approve me?
Oh, okay? You can't hear me again.
I can't hear you. I'm going to try to leave and come back.
Okay. Yeah, I apologize for these technical difficulties. I just let Deepa back in. Okay, now can you hear me? No.
No.
Afraid not. But I think.
Let me try one more time, okay?
Okay. Okay, thank you, Dasandra. Apparently the participants can hear me. So while Deepa's trying to get in, my question was, for ELA, social studies, science, and math, which of those 4 disciplines do you think most effectively engages reasoning, discussion, imagination, and creativity? And it may not be the same discipline.
So Cassandra says all. Jenna says math for reasoning. And Rondalyn, right? Math and science for reasoning is 1.
Okay, good.
I wonder. I would agree, right? Math particularly for reasoning, 1. That's what I would say.
Let me give you the disappointing information. When I go into schools and I first meet students, and this is both middle school and high school, and I ask this question about reasoning with the students, I frame this as thinking hard and critically about the subject matter, having discussions, engaging in interesting discussions about the subject matter, opportunities to use your imagination, right, and even be creative. Unfortunately, mathematics, in the polls I've made of students when they first come into the project, never rises to 1 or 2. And you have to remember, I'm particularly working with students who are performing in the lowest quartile, right? Which in any district can be a large percentage of the students. But they do not experience many opportunities to reason, think critically about the mathematics. As a matter of fact, it's their impression that there is no reasoning in mathematics, that it's more an issue of formulas that you follow. There is very little discussion, and they often look at me like, "Sir, what's the matter with you?" When I suggest that imagination and creativity could be a part of the mathematics classroom. Now, ELA, English, whether it's writing poems or rap, they see that there's a space in usually their English class where there could be an engagement around imagination and creativity. But in the mathematics classroom, it's not seen as really having the space for such. And in the Algebra Project, we're really trying to create the space so that those 4 qualities that I mentioned are seen as being intrinsic to the doing of mathematics. I would like to tell you a little story about what happened when I was in an Algebra Project classroom. And for that, I have to go back to, what do you call it? My
share screen?
Yeah, I have to share screen.
Meanwhile, any questions for Bill that I can start noting down? Thoughts that you would like to understand better? Please start putting them on chat. I'm eager to ask them. Okay.
So I was in an Algebra Project classroom. This was actually a 9th grade classroom. They were doing Algebra 1, and the Algebra Project was being inserted, into that process. Before they began the Algebra Project work, the teacher had put this equation or an equation very much like it up on the board and asked the student to come and solve it. And what's important about this equation is that the unknown quantity x is being subtracted from some number from 10. And the student came up, and of course she knew, well, I either have to subtract 10 or add a negative 10. And she did that to both sides, and then had that second equation that you see there, right, with the subtraction sign x is equal to negative 30. And she really wasn't quite sure, she wasn't sure what to do at all. The teacher worked very hard at being Socratic and not just telling her, well, divide by -1, right? Asking a series of questions, which seemed like a long time for me. It must have seemed like it was forever for her. She finally got down to the point where she wrote x is equal to 30. Now, I'll come back to that problem in a moment. But before that, I would like to really talk to you or show you what process we've actually developed in the Algebra Project for the way in which we engage students in mathematics. This, you'll see in the literature, Lewin, Piaget, Kolb, it's called an experiential learning cycle. And you see at 12 o'clock, there's some concrete event. At 3 o'clock, that refers to reflection upon that concrete event. At 6 o'clock, what we're denoting there is some abstract conceptualization from that event? What ideas do we draw from it? And then at 9 o'clock, we're looking at an application which will take us back in this cycle to a concrete event again. So it's really, as a learning cycle, meant to act as a spiral. Now, in a very traditional mathematics classroom, the process of teaching math often begins below the 3 o'clock position, moves to 6, and then moves back over to 9. And by that I mean, very often the children are given a mathematical concept and its rules, such as in order to add or subtract integers, here's the process that occurs. If it's subtraction, you change it to addition, and there are a series of considerations once you've made it into an addition problem. Those rules are often given, an example is shown, and then students in moving from 6 o'clock to 9 o'clock try various examples or exercises involving those rules. In the algebra project, because we're dealing with a population of students who think, for whatever reason, they cannot do mathematics, we do not start at that 3 o'clock position, but in order to give all students access to the concept that we want to develop, we start with something which they all have access to, such as a concrete event. If you have a chance to look at Bob's book called Radical Equations, the appendix to that book is really a detailed description of the kind of lessons that we do in the Algebra Project, and in particular, a concrete event which is central to learning algebra. And that is that a concrete event which we often use is the idea of a trip. In a city with a public transportation system, actually in the 90s, we were working in Atlanta. And again, about 4 or 5 years ago in 2015 to 2017, I think, we used MARTA, right? The subway system. The students go on a trip on the subway. That's the concrete event that they all experience. They share that experience. And that event necessarily needs to be of interest and engaging to the students, right? They need to make the connection with that concrete event. They come back to the school, and the work that they do in coming back to the school is, in a sense, representational. We ask them to either create a picture or a model of that event. If there's a coordination with the art teacher, say in middle school, students would actually construct a large mural, right, of the trip. We call it a trip line, and the various stops, right, that they made along the trip line, and anything that they found of interest in that trip. That's the first representation that we ask the students to create. And actually the word itself, that's the first representation, right, of the event that the students engage in. We ask them to talk about what was interesting in the trip, both at the level of small groups or teams and at the level of the entire class. This idea of people talk involves not only they're talking about the event, but they're writing about it. And it's not in a particularly mathematical way. That first quadrant from 12 o'clock to 3 o'clock really needs to be owned by the students. It needs to be their interest and ideas that are captured, right, in this learning cycle from 12 o'clock from the concrete event all the way down to their reflection in people talk. So if you walk into an Algebra Project classroom, you will often see it. The classroom is plastered with chart paper on the walls, and the chart paper on the walls is how students in their team publish to the rest of the class their ideas and thoughts about whatever that experience was. From that foundation, and that it's a foundation in the sense that what we've seen is the ability of students to make that jump, that abstraction from the concrete event to the abstract concept. The foundation for students making that transition really occurs in that first quadrant, right, from 12 o'clock to 3 o'clock. Students who normally do not talk about the mathematics, under those conditions, they have ideas which they are willing to share about that trip and that event. At this point, we actually make a transition which often students aren't aware of. We begin to talk about the features of that event. What features of that event do you feel are important? And how you think those features are related to one another. In the example that I'm about to show you, we're going to consider this idea of a trip, as I said, either on the MARTA, the subway system. In places where there is no subway system, the kids take a trip really through their neighborhood or through the city on a bus. Okay? So they talk about the features of the trip, and they then cast those features in their own symbolic, iconic, or diagrammatic representations. And the idea is that they can really make those representations of their own creation. There's an element of creativity here. Do the same type of meaningful work that the conventional symbols of mathematics do. And we'll see an example of this when I get back to that, to the little case study that I presented about the student. But let me give you a sense of what feature talk is about. So what we're really doing is creating what you could call an experientially grounded metaphor for the trip. Metaphors are critically important cognitive structures because a metaphor allows you to understand something which you might not be clear about, to understand that in terms of something that you do understand, that you are grounded in. So this question of what makes a trip is actually what I would like you to answer, if you could, in the chat, right? Put in a couple of recommendations. And what I'm really asking there is, what makes a trip is people talk. The kind of feature talk which we do not use with the students yet. What are the essential features that any event must have in order to be considered a trip and not something else? And I think the amazing thing about this question is, if it can be answered, there are deep mathematical consequences in the answer. Let me close this down for a moment. And go back, back on the screen. Yep.
So the question is, generally when we go on a trip, what are the key things that you would think needed parts of a trip, kind of anatomy of a trip, if you will?
Right. What are the essential features of a trip? And now, may I say, if you name something, right, then the test is, well, if we take that away, is the event still a trip? Right. So it's a simple question, but the answer or the responses can be held to a much higher standard of rigor, right, than the initial question. Are there any suggestions there? What features must an event have to be a trip?
So we have Rondalyn saying mode of transportation.
Exactly. Go ahead. Yep.
Activities. Yes.
Good.
Experiences.
Good.
And of course, you have to come back home, I guess. Settings?
Setting,
Yes.
setting or context, experiences. Hmm. Well, I don't know. Do you have to go home?
Events, experiences, for sure, right?
Mhm.
Settings.
Yeah, and I should let you in on a secret, because the kids come up with a very long list, right, of features, and none of them are wrong. I mean, but you can use those features to get the kids to talk about this concept of a trip. Now, that's not only has an interesting piece there. You could do a virtual trip, so you may not need to leave home. And actually, under the pandemic, when we were doing this little piece of Algebra Project curriculum, we had to do it online. And that's exactly what we did. We used Google Maps and we took a trip. And unlike a trip around the neighborhood, this was a trip across the country. Right?
You could go anywhere around the White House.
Yes, yes. So here's the thing. Asking a question like that gives kids, particularly kids who think they can't do mathematics, an opportunity to answer a question and not be penalized because either in terms of grade or social standing because they're wrong. It opens up a field of discussion among the children. And we end up with a long list of features of a trip. Now, what we do in the project is actually 3 of those features we use to develop a little piece of mathematics that I'm going to show you. But any of those features could be used as a basis for the mathematics. And what Deepo, it was interesting. The first thing that was mentioned, this mode of transportation, Rondell and Pickney. Thank you very much for that, because there is an Algebra Project little curriculum unit called road coloring. And Alan Shaw, who's in the computer science department at KSU, he was the PI. He's the PI on this grant. And the previous one, he created a little app around road coloring and what's called the road coloring problem. And that little piece of mathematics, which is really used as an experiential foundation for the mathematical concept of a function, that mode of transportation feature that you mentioned there is central to both the unit and the app, right, that Alan created. And perhaps in another workshop, we'll actually be able to show you some of the work that was done around this. But let me go back and catch the PowerPoint. So you see the PowerPoint again?
Yeah, perfect.
So here are the features that we use initially. The idea that what makes a trip, there are many things that make a trip, but 3 of the very, very basic things that make a trip. A trip has a start, a finish, and movement. And while we use this to build a specific piece of mathematics, I would like you to see, even these features can be debated. And what we want students to do is to really, it turns out the kind of exciting discussions that students have almost, hopefully in their ELA, in their English class, you can get those same types of discussions going in a mathematics class when the abstract mathematics is grounded in something, in an experience which all students have access to, such as a trip. It turns out that these 3 features of a trip correspond to exactly the three features which define, in some case, you could call it advanced abstract mathematical concept of a vector. Now, we don't mention vectors actually in the middle school or, in Algebra 1 or geometry, but the diagrams that students are making based upon those features are exactly that. They would be recognized by any mathematician and physicist as a vector. So this idea that a trip has a start, a finish, and a movement that takes you from the start to the finish, you can capture in two equations. An addition equation where that plus sign means something. Now, you'll remember, I can barely remember it, but in elementary school, the first meaning of the addition sign that I had, that I got as a child, was plus means put together. In the formulation of signed numbered arithmetic that we develop in the Algebra Project, plus means move. And the number that follows the instruction to move is a signed number. It may be -3, +4. The sign tells you whether to move to the left or the right. And the number itself, the whole number, tells you how many units to move. So if you start at B, and in this case, if you move C units to the left, that is equal to a finish at location A. So what we've done is, this feature talk has allowed us to construct a way of interpreting the addition of signed numbers, which makes sense to kids because the idea of a trip makes sense to them. Now, that subtraction equation, while in the middle school, in the elementary school, we're usually told subtraction means take away. Part of the problem there is you can't take away something that's bigger than what you're taking it away from. There is another model which covers the cases that takeaway does not, and that is comparison. And we use that model all the time if someone's asking, for directions to someplace, right? The directions that you give, when you give the directions, they are a virtual movement. And if they follow the directions correctly, they will become a real movement. But in order to give the correct set of directions, you have to know where the person is going to start, the location of the start, and the location of the finish. So for that equation on the left, the way the kids interpret that is the finish, which is at location A, compared to the start at location B, is the movement. So many units to the left. So under this idea of a trip, for every trip, there are these two basic ways of describing the trip, either by talking about the move that you make from the start, or by talking about what happens if you compare, if you compare the finish, if you look at the finish compared to the start. And that student who was at the blackboard that I mentioned earlier had been working through this unit called trip line. And so she was able to read that subtraction equation from that perspective. And here's what she told me. Well, she said it's 10 minus x is equal to a -20. And I asked her, can you draw the picture that corresponds to that equation? She drew a number line. And she said, that means that we're starting at x, and we're going to finish at 10. And the way to get there, from x, I have to go to the left 20 units. So she drew that picture. And her language wouldn't have been that exact, but the finish of the trip at 10 compared to the start of the trip at X is 20 to the left. She understood that trip, and she understood that she wanted to find that location X. So she used her imagination. She added something to the picture which was not there. And that was, she thought, well, I know how to get from X to 10. If I start at 10 and I do the opposite, I go to the right 20 units, I should end up at X. And that means that X must be located at 30. And let me tell you the punchline to this story, because she was standing with her back to the classroom, and she looked, you could see her look at the picture. And then she looked back at the calculation that was done. And she looked back at the picture and back at the calculation. And then she turned around, she pointed to the algebra, and she said to me, Mr. Bill, why would anybody do it like that? And I have to tell you honestly, my response to her was just that. Honestly, I don't know. But I can tell you what we really want is for students to be fluent in moving between the calculation that you see on the right and the picture that describes the calculation, right, on the left. That's the kind of fluency that they read an equation, and they're not just reading character by character, 10 minus x equals negative 20, but that they can do an interpretive reading of that equation. So what I've described to you is the process that we've used that we've developed and used in the Algebra Project for helping those students who think they can't do math, right? Read and understand the symbolism of mathematics. Over the past, really, I guess it's been 6 years now, in working with Alan Shaw at KSU and his team, right? Deepa and Brian and a couple of other people in the greater Atlanta area. What we've been thinking about is how we can use that foundational process, this 5-step curricular process that comes out of the Algebra Project, and tie it into the foundational learning that all students now need to do in computer science, and in particular in computational thinking, right? And what we've recently received a grant from the National Science Foundation. We're calling it CS for Algebra. We are working with a middle school in Clayton County. In this year, the 6th, it's a 3-year grant. We'll be working in the 6th, 7th, and 8th grade. And if you see in that third quadrant between reflection and abstract conceptualization, it's in that quadrant that we're tying together this idea of feature talk and multiple representations with this CT process, right? And Deepa is critical to helping us both explicate and tie these processes together, right? So this idea of decomposition and pattern recognition and abstraction. You notice feature talk is, in a sense, it's a process of abstraction, which is moving the critical features of the event to the foreground. And as Deepa has taught me, the features in the event or the problem that are not critical to its expression and solution are moved to the background, are hidden. Right? So we've just in the really year that we've been working together on this, we've actually found some deep connections between these two processes. But I think what's equally important, you notice that that process of computational thinking moves across two quadrants. It's also moving into this space between the abstract concept and its application, right? So this process has given us additional features to work with in terms of algorithmic thinking and the impact of what we're doing in that upper quadrant that we call an epistemic playground. We're referring to it as epistemic because the applications that children bring back to the concrete event and what the concrete event that they will be working with is actually a simulation of a concrete event. It's in a micro world that they can manipulate and play with. It's really for the purpose of the students increasing their knowledge of through that application and beginning this learning cycle again. The research that we'll be doing is particularly in that epistemic playground to see how intertwining these two processes can make that playground a place where students have rich discussions in mathematics and computer science, a place where thinking, critical thinking and reasoning is at the center of what students do, and a place where imagination and creativity are central to the activity of students, which, as I said, though we as adults, administrators and teachers may think that that is a natural piece of the learning that ought to occur in mathematics, from almost any survey you could take, and I advise you next week to ask some kids. We're not to the point where students perceive that as integral and important features of mathematics. The one piece that I want to end you with before we talk for a bit is here is the team from Kennesaw and from the Algebra Project, and it was really a pleasure to have this opportunity to talk to you about our work.
Outstanding, Bill. So questions, folks, please type away. Something, right? Fantastic. When you think the impact it has on these children. So please put your questions away. I had one. The piece on the, if you could bring that chart back up, either one of the two, and expand a little more on the people talk part. It seems like as if you're encouraging conversation among students in the classroom, and it happens early on. So exactly how does that fit in a math computer science classroom?
Okay, let me share a bit. And we're moving, back to here. Okay, you know, as I said, I think it's only been over the past 20 years that computer scientists have liberated themselves at the university level from mathematics, right? And they've demanded, their own department and their own chair, right? And actually within NSF, their own funding. So, this a grant that we received, it's from Education and Human Resources, but it's their Computer Science for All program, which is separate and distinct, right, from mathematics education. So they did have a common origin. I think what they also share in common is an artificial language. For mathematics, the algebra, as I said, that students read, the way they typically read the algebra is character by character. What we've seen is giving them the ability to do an interpretive reading of mathematical symbols. It's really creating the language to articulate a language which is never spoken. The conceptual language of mathematics typically isn't spoken, right? When people read mathematics, unless you're a physicist, you read it character by character. And this is why I emphasized the difference in the beginning, because in physics, we really did not read, undergraduate and graduate school, we did not read mathematics character by character. We did an interpretive reading of whatever equation we were working with. If it was written F is equal to ma, right? We talked about the forces that were acting and the resulting acceleration, but we didn't simply read that character by character. In computer science, programming, for example, coding, is also, it's not a natural language, it's an artificial language that is read and is written, but is never really taught. No one really, even Unix programmers in the past that I've worked with, they never spoke Unix. In each instance, what we want students to do is to develop the kind of fluency that allows them to do an interpretive reading of symbolic representations, whether the symbolic representation is an equation, an inequality, or a section of code. And what we've seen is that the foundation for that type of literacy is what happens in that first quadrant from 12 o'clock to 3 o'clock. That, with language, you say a sentence and it is gone. I may remember what you said a moment ago, but it's gone. We first ask students, whatever they're talking about, to make a picture or a model of that, so that when they talk, they can point to what they refer to, right? The picture or the model is not gone, and the picture or the model often removes certain ambiguities, right, when students talk about their ideas. So that picture and model is important. That needs to be there in place because it's permanent or semi-permanent. And the other piece is the people talk. That if you think about the example that we did with the trip, it's the fact that kids talk about the trip, are excited about the trip, are engaged, right, in that discussion, and the debate that ensues around what makes a trip, that lodges those three ideas, a start, a finish, and the movement, into their minds and into their memories. So what we've seen as an empirical matter is what happens in that quadrant from 3 to 6, and what happens in the quadrant consequently from 6 to 9. It has a foundation in people talk. One experiment I would like you to try is if you go into a classroom where the students, those students that we characterize as being the best in, say, mathematics, but I think this would also hold in computer science. If you go into a middle school and you ask them about, say, an equation, the best students can tell you a few things, right, about that equation, and they can certainly read it character by character. But at a certain point, the knowledge that they have of that one sentence, that one equation, it at a certain point it's inert, right? After they've read it, if you don't ask them to solve it, there isn't much more you can say about it. What we've seen in the Algebra Project is because of the people talk that students have done in the classroom with each other primarily. The people talk is primarily between students in their ordinary discursive modes. If you ask students about equations, they will talk to you about the equations to the point where You have to say, okay, yeah, I think I get the idea. Thank you very much. Right? But,
Bill,
go ahead.
Bill,
Yeah.
didn't mean to cut that, but it seemed like a good breaking point because we have a very, very good question here that I think is going to absolutely excite you. I'm going to read it. Nathalie, I hope I said your name correctly, Damus, asks, do you have any information on how the Algebra Project could be used with adult learners? I am specifically interested in how the approaches discussed could be used to assist adults that have had a history of negative experiences in mathematics classrooms. I'm sorry, you only have 2 minutes for this answer.
And the answer is yes. And you can send an email. I can tell you more about it. Typically, when we're working with a school, one of the important processes that occurs is we have family nights. The kids come usually in the beginning, at the end of each quarter with the grading. We like the parents to come and for the students to explain the work they've been doing to the parents. In these workshops, we've also given parents an opportunity to work through some of these issues. And one of the things that parents conclude is, for example, this whole piece about a trip, right? Interpreting trips. My God, if I can do this, my kid who isn't supposed to be good at mathematics can probably do it too. There's an issue in moving parents to the position of advocacy for their children. But I'll tell you, in the early 2000s, Bob Moses and another member of the Algebra Project, Stafford Broussard, held a series of workshops in New Orleans, not Los Angeles, in New Orleans. And the workshops were mostly attended. There were some parents, but also it was built around a group of community organizers. And these were people who weren't particularly, good or even had positive feelings towards mathematics, but they, in a sense, got an opportunity to look at the mathematics not from a computational perspective, but from a more philosophical perspective that made sense out of the mathematics. So the teacher training that we do is run in the same way, right? It's an opportunity for teachers to discuss the mathematics, to go through the experience and discuss the mathematics in a different fashion. So yes, indeed, I can give you more information on that, but we have been using this same curricular process with adults, with college students, and with students in the K-12 system.
Excellent. So any other questions? Bill, I went ahead and put our email addresses,
Great.
both our addresses up there on the chat. Absolutely. We are very excited for this collaboration, if you will, between Kennesaw and the Algebra Project, as well as really bringing meaningful mathematical experiences along with computational thinking into the middle school classroom. So please, we are anytime available to help. Bill?
Yeah, very quickly. My greatest hope is, we've started this computer science for algebra project is next year at the next year's conference. I would really like Alan Shaw, who's the project leader, to come to really give you an opportunity to both see and hear what we've done around mathematics learning and computational thinking in the classroom. That will be some exciting stuff.
Absolutely. And please be on the lookout. We plan to have a lot of conversations and maybe even hold a mini conference where we'd like to invite folks, from administration and teachers from the classroom to show you the work that we are doing with our current teachers and with our current administrators at Clayton and in the Georgia DOE. So please be on the lookout. We are on to really exciting stuff, and we are going to make a difference, and we hope you will join us as well. So Bill, first, thank you very much, sir. Thank you for all that you've been doing for our kids, for math, and now for computer science. Thanks for taking this time. I know how much time and effort you've spent to make this a success. So we really, really appreciate you. Thank you, everyone, for coming. We really are honored. You had many choices and you came to ours. We hope we answered as many as questions as you had. We've tried to keep it engaging. We're going to try and leave you off in 3 minutes late, but not too late. But please, with our email addresses, we try to return emails as quickly as possible because honestly, we both are very excited and about it. So thank you very much. Thank you for coming.
And thank you, Deepa.
Yes, yeah.
Good.
So I'm going to go ahead and leave because the recording still goes on. So.
Oh, okay. So we'll catch up.
Yeah.